Hey everyone, just a short demo video here, catching up with the polynomial regression and the ideas of regularization and bias-variance tradeoff all in one not so big Jupyter notebook. So it's a little bit complex and you can draw out different topics all in the same notebook. So let's just go ahead and try to hit all those in a reasonable amount of time, shall we? Okay. So we are starting from the same infrastructure that we've been doing the last couple of demo lectures, right? We're going to go ahead and create a set of toy data. This time we're going to be using the sinusoidal function, right? So let's go ahead and execute that. Now, a reminder, to make something sinusoidal, we're going to have to fit a regression which has polynomial terms, would be the easiest way to do this, right? And we've seen already that we can create something using the polynomial features preprocessing element from scikit-learn, right? And this time we're going to call third degree. Okay, we're just going to go ahead and create a set of features just to show you what they look like. All right, what do they look like? Well, as before, we have a column here, this first column, which is a bias term, right? It's just a 1. And we're going to do 1 plus x squared plus x cubed as we go across the columns because we have a third degree polynomial. Okay, so for the x data points that we've made, we have 0.11, 0.22, etc., 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 all the way up to 1.0. Those are our x's. So the stuff in this third column, this is the x squareds, right? And that goes all the way down. Right, so we just took our x's, which were just column number 1 here. Okay, this, and by 1 I'm using 0 indexing. All right, for those of you who are not computer sciencey, when you start counting in many computer languages, you start counting at 0. So this is column number 0, and this is column number 1, and this is column number 2, and this is column number 3. Okay, just to be ultra clear about what I'm talking about. When I say column number 1 is x, that's the column I'm talking about. All right, and Python, like many computer languages, is 0 indexed. The first element is always the 0th element. All right, whatever. The point is that here we go. We showed you an example of how you can fit a polynomial feature starting with just that first column, right? Which is just the x's that came in to create this sinusoid. All right. Now for that, let's go ahead and show the data points and show different regressions on these data points. So we're once again just drawing 10 data points, right? That's what we saw right here. 10 samples, 10 x's and 10 y's that are the sinusoid corrupted by a small random noise. All right. Well, what we've done here is we've looped and we're just going to check out a few polynomials. We're going to check out polynomials of order 0, 1, 3, and 9. So each time around, what we're going to do is we're going to create polynomial features of the correct degree for doing our regression. Once we've created new features that are the correct order, well, all we have to do is go ahead and fit our model on those features from the training set. Okay, we'll get a set of predictions and we can plot those predictions. So the true function generating things is in green. The blue is the random noised y values that come from that underlying green function plus noise. And the red is the fitted curve. That is the result, the predictions. Okay? So what can we see here? Well, the easy one is that the 0th order regression is a regression which is only fitting the 0th column, the bias term, right? That's all it's fitting is the bias term. And when all it's fitting is a bias term, what it ends up learning is where is the mean of y in this training data. So that red is the mean of the y values across the training data. When we fit a first order, we're fitting a 1 plus x and a 1 plus wx, a bias plus an x term, right? What we're finding is a linear regression like we've been doing before. Okay? When we fit a third order polynomial, then we are fitting the squared and the cubic term. And in a 9th order polynomial, we're getting to x to the 9th power. All right, what are we seeing here? Well, the 0th and the first order are, you would have to say, clearly underfit. They are not capturing important aspects of that green line, right? So they're not accurately capturing the process. These regressions don't have an ability to get complex enough to fix our problem. So the third order polynomial looks decentish, right? It gets towards the idea of what's going on in that green line. Now the 9th order polynomial is clearly overfit. All those wiggly lines, you know that if you drew a different set of data from the same process with a bit of noise, you would be missing potentially by quite a long ways. Okay, well, let's take a look at that idea of what would happen if we drew new data from the same process, right? What if we have not just the plots we've done here so far, but what if we draw 50 new data points, right? 50 test set or 50 validation set data points, depending upon what we want to do with them. Well, so we have the same plots this time, but we have the addition of some random data from the process, 50 new points. So those 50 new points fall in the yellow, okay? The blue and the red are exactly the same as what we saw before. Right, so you can see, for instance, that that 9th order polynomial is missing quite a lot over here, right? These, and so on and so forth. And if we can, you can easily see that if we took that 9th order polynomial and we extended it for another period of the sinusoid, well, it's going to be ridiculously bad, right? Okay, so we can pretty much by eye tell what's overfitting and underfitting. But why is that? Well, as I mentioned during lecture time, what's happening here is that the underfitting is happening because these low order polynomials have a lot of bias. They are biased towards what the solution should look like. They know exactly that the solution is going to be some kind of line, either with a horizontal slope or with an arbitrary slope in the case of m equals 1, right? And they're going to always interpret the data that way. Because of that bias, there's a lot less variability. If you draw a new random data set with the same, with those yellow dots instead of the blue dots, the mean of the yellow dots, or the slope you're going to get from fitting the yellow dots, they're not very different, okay? The noise is of a pattern which means that different draws from the same random process don't really yield very different answers about the mean of y, or the proper slope of this. Okay? In contrast, the ninth order polynomial is highly variable. If you fit it on different subsets of 10, you would get ridiculously different answers on the shape of that red line. Each time you do that, you're going to get a variable answer. And it has no bias. It's not biased to find a particular solution, right? It's willing to shape itself to whatever noise is in the data it's trained on. So this is the bias-variance trade-off. When our algorithm is more biased, it's going to be inherently less variable. And that's variable in the sense that new data is not going to give you a very different answer. But when our algorithm is highly variable, when it's complex enough to overfit, it's going to be variable on every fold of the data. And it's got no bias, no oomph to push it towards a particular kind of solution. So it's willing to drape itself across the noise. Okay, so that's the bias-variance trade-off by eyeball. Let's see it in a more quantitative way, okay? Hey, here comes the cat. Did you wake up from your nap? Nice. Okay. So, an easy way to do this is given to us in scikit-learn. So we can take a metric and we can show, as we go with different levels of the model, different orders of the model, that's what I'm trying to say, we can see the training and validation set errors. Okay? So that's what this little loop does. We're going to loop across model orders 0 to 10, and we're going to each time create the polynomial features properly, do the regression, find the errors. Okay? So let's take a look here. So with 10 training samples and 50 validation samples, right, we're going to get training set errors that look like the blue line as we go from 0th order up to the 9th order. Okay, so what are we seeing there? That training set error line is continually decreasing as we get more and more orders of magnitude into our polynomial. We're always getting better at training set error. Well, you can see that up here, right? This has got a lot of training error. It's pretty far off the blue dots, that red line. This is, in 3rd order is a lot closer to those blue dots. But at the 9th order, we can go exactly through those blue dots, straight through the middle of them, because we have enough degrees of freedom at 9th order polynomial to fit 10 dots perfectly. Okay? And if you just kept going out here to 11th, 12th, and 15th order, your training set error would stay at 0. It would be perfect. It would never get worse. But that is in stark contrast to the red line, the validation set error, right? The validation set error gets better as we get more orders of magnitude, but around 3 to 5, it's pretty much, 3 to 6, it's pretty much about the same thing. But then it starts going up at 7th, 8th, and 9th order. Okay? The validation set error will continue to get worse if we went up to ridiculous orders, potentially. So you can see here underfitting. Underfitting is where we have not yet gotten to our best validation set error. Overfitting is where we start to get worse again, right? We are overfitting the noise. And so you can exactly see the overfitting and underfitting regimes. And you can see where the bias-variance trade-off is sending us back and forth across the error surface here. Hi, kitty. Please don't claw my leg like that. That hurts. All right. and say hi at least. All right, go play behind the computer. Okay, so here we go. How can we solve this, right? Is there a way in which we can take a highly complex ninth order polynomial and prevent it from getting into this overfitting regime? Well, we can. And that is a process called regularization, where what we do is we try to prevent an algorithm that's capable of a very complex solution from getting too complex in its solution. Okay? So what we do is we add a penalty term, and we discuss this in lecture. So here is the normal loss function, right? This is the residual sum of squares in a matrix notation. We have the errors, the predicted value minus the true value, right? And we square that, right? We have that times itself. The transpose is merely for the fact that we need to sum these up, and we need to do the matrix math in such a way that what we get is the sum of these squares. Okay, so that's your residual sum of squares right there. To add a regularization, what we do is we add a second term, and that term is going to be a function of the weights themselves. So when the parameters can all of them get arbitrarily large, we can get very complex solutions. But if we force, in this case, the sum of the squares of the parameter vector to stay low, what we are going to do is we're going to be squishing the weights down and preventing those weights from growing large enough, and especially large enough in all of the parameters, so that we could get some sort of really, that would prevent us from getting some sort of really wacky solution, right? Okay. So in this case, we normalize by the L2 norm, by the Euclidean norm, right? And when we change this parameter lambda, what we're changing is how much the loss function cares about the regularization term. When lambda is very large, this term on the right, the regularization term, has a lot of influence, and it's going to try really hard to squish the weights. When lambda is very small, this term on the right is small compared to the misclassification, right? Sorry, not misclassification error. Compared to the residual sum of squares, right? The residual sum of squares will have a much more dominant magnitude, and we will try not very hard at all to squish those weights down. So it so happens that you can solve this closed form. It's still in ordinary least squares and the residual sum of squares. It's just that we get, besides this part, which you're used to, we get a new part which has the lambda and an identity matrix in it. Okay? So obviously, again, that lambda getting big is going to create more squish. Right? We're going to try to force the answer to be closer to the identity matrix and not get too crazy. It's going to force things to go towards 1. All right. While I mentioned to you here that there is a closed form solution for this kind of regularization, I'm not going to make you do it in NumPy, because scikit-learn makes this a little bit easier. We are just going to grab something called the ridge regression. So the ridge regression is just a name for this loss function up here applied to a regression, the one we've been talking about. This is ridge regression. Another term you may hear for the exact same thing is Tikhonov regularization. But either way, we can just go ahead and, instead of applying the ordinary least squares, we can apply the ridge regression in what is otherwise the identical code to the code we had up above. Okay, so the only difference is that now we call ridge with a lambda argument, whereas before we were calling linear regression. Okay, so when we do this, what are we going to see? Well, so actually there is a code difference here. I forgot to say that. Instead of looping over the polynomial term, okay, how many orders the polynomial is going to be, we're going to do everything at the 9th order polynomial. But what we're going to loop over is the magnitude of lambda. So lambda is going to start off as 0.1, and we're going to progress through a few orders of magnitude towards 1 to the minus 9th, which is a very small number, which might as well be 0. Okay? So let's start down here on the lower right. So again, every single one of these panes is the 9th order polynomial, which we know to look like this, right? The 9th order polynomial is all kinds of wiggles. Okay, so all 4 of these panes in this graph are 9th order polynomials. But here we have a regularization parameter, you know, that lambda is basically 0. So basically that right-hand term has no effect. So we are basically unregularized, and we're seeing pretty much the same solution as we saw as just a plain old straight 9th order polynomial. Overfit like heck. Okay, but as we start to ramp up that regularization constant, here it is in the 10 to the minus 6 range. Here it is at 10 to the minus 3. We are seeing actually quite a lot of squish. So we're seeing that this is no longer overfitting like heck. These look a lot like the 3rd order polynomial solutions, right? And when we get it close to a 10th, we're seeing something that's even approaching like a linear, like a 1st order kind of looking thing. So we're really putting on the regularization in this one. Okay, so this kind of regularization enables us to take something that normally has ridiculously high variability, high variance, and it's allowing us to make it a more biased thing that is trying to find a simpler solution. We're biasing it towards simpler solutions. Okay, so this kind of Euclidean regularization using the L2 norm is just one possible kind of regularization. So we did this, the ridge regression, the L2 regularization, right? That's the term that's trying to squish the weights. But you can do any function of the weights that you would like to try to do this. So you will quite often see something called lasso regression. The lasso is an acronym, and don't even worry about that. Now, if you go into some more statistics, you'll understand some of these words. But the lasso uses the L1 regression. Okay? The L1 regression has some, regularization. The L1 regularizer is, oh, there goes my camera battery. That's super cool. The L1 regularizer is just going to try to sparsify things more, okay? So whereas L2 is trying to regularize the sum of the squares, L1 is trying to minimize the absolute values, right? And there is a bit of math which I can't kind of gesture for you to show you because my camera just went out. But fundamentally, what L1 tends to do is sparsify. It tends to drive parameters that are near zero completely to zero. Okay? It doesn't keep things balanced. It tends to just drop out less important features completely. And by producing such a sparse solution, an L1 regularizer can be quite useful for finding subsets of features, right? You can use it to select the best features for solving a problem. And lasso is very often used in that sort of a way. Now, you can combine these two together with a technique that's known as the elastic net. So in the elastic net, we have both an L1 regularization and an L2 regularization over here in this whole term. And there's a balance parameter, which I'm calling alpha here. And that alpha just controls how much of the regularizer is dedicated to L1 and how much of the regularization is dedicated to the L2. All right? So, what should you take home here? You should take home the idea that there is a bias-variance trade-off. And when your algorithm is way too powerful, you can overfit your data because you're allowing too much variance and you're losing the bias towards particular solutions. You should take home an understanding that you can make graphs that look like this to show you when you are underfitting and when you are overfitting. We can vary parameters to show us that, hey, this may be the regime that does the best because this is where our trainings or our test set or validation set error is the best. Okay? So, and one way in which we often approach this situation in machine learning is rather than looking for the optimal complexity of model, we can also, instead of playing this game here and looking for model order, we can start with a highly complex model and just add a regularizer to prevent overfitting. But that is also a parameter. Okay? So, a couple of different ways to skin the cat here. Nope, no cat around, so he doesn't have anything to say about that. And I hope that you find these notebooks useful, both for kind of demonstrating once again the things that we've been talking about in lecture, but also showing you ways to implement. And we're going to get into more and more implementation as we advance in the weeks here. All right. Thank you so much for your time and attention. I'll see you next time, maybe with a charged camera battery. Hasta.